The title of my talk is Estimating Peer Effects from Network Data. It's a nice way of analyzing network data in the social sciences. So I'm talking about social networks. And peer effects are basically summary statistics of how the network is working, how the network is affecting individual behavior. This will be a little bit different from what computer scientists do in network analysis, who usually look at the networks and structures of the networks. Here it's about how a network is affecting behavior. So we're looking at a larger set of variables, and the network is just the mechanism with which people are connected and interact. Let me start with a little bit of notation. So here's a very simple network of just 4 agents. Let me call them agents. That's neutral. That could be animals, could be humans. In my application, I will study later on network behavior in classrooms. So it will be high school students. So there is a network of those 4 people, and just for the notation, if the arrow goes from 1 to 2, that means person 1 is assigning person 2 as a peer. In other words, mathematically, 2 is affecting 1 as a peer. Yeah? And they are related in that fashion. If 2 changes its behavior, 1 is also changing its behavior. And we can represent such networks with a typical adjacency matrix. For that little network here, it's the adjacency matrix A, and what will become important later on will be the row-normalized adjacency matrix G, which is just always divided. We divide every row by the number of ones in a row. What is different, maybe from the usual network graphs, is that we don't have the network information, but in addition, we have covariates or features, yeah? Variables that are affecting that behavior of individuals, the x's, and we have latent factors, right? The e's or epsilons, unobservables, which also affect that behavior, and which may be jointly affecting that behavior, like weather or something like that. Some general conditions which we don't measure, but which are definitely there, but we don't have that information on that, or we cannot model that. And the question is now, how can we separate those effects? What is the difference between, say, just a graphical analysis of networks and the econometrics of networks? So it's a mathematical statistical model of networks. First of all, we have an explicit definition of a stochastic process. So the usual approach mathematical statisticians have, they define what is exogenous, they define what is endogenous, they define the stochastic process, the error terms in the process. The advantage is, of course, that you then can do statistical inference. Once you're estimating those network connections, you can do inference and test whether that connection is significant or not. The third point I mentioned already is that we want to learn something how the network is affecting individual behavior and want to measure that. And the final point is the structure of the network also affects the properties of the estimators. That will be a very serious methodological problem. We will see that dense networks, for instance, have serious implications on the estimation process. So We have to get to a mathematical model rather than the graph, and that would be such a representation in terms of this adjacency, the normalized adjacency matrix G. So we have kind of peer effects. You see, Y is vector of outcomes. You have n agents you want to describe, and the n agents, they are affected by the activity of the other agents. Here in this neural normalized notation, it would mean that the person I, or agent I, is affected by the average person of its peer group. Yeah? So the G defines the peer group, and through the normalization we get the average, right? There are exogenous effects, there are exogenous peer effects, and the unobservable factors. So what are exogenous effects? Well, in the study I'm going to present later on, it will be some features of the school class, for instance, the education of the parents, which affect the behavior of the students. So Y would be the student's performance, but there is also effect of the peer group, the parents of the peer group, which affect this behavior. Okay? And so my outline will be, first I will talk about some of the fundamentals of this approach, that is the distinction between causality and correlation, about the identification, and then the weak identification problem that arises in certain networks. I try to be as non-technical as possible, and then I will show you that the network information can be used to identify these causal effects, and then I will present you an application from educational attainment, and then we have some ideas about extensions. So the identification problem is, why are two people behaving similarly? Yeah, that could be, there are endogenous peer effects. They are in a research cluster, which is also something like a network. There could be exogenous peer effects. Yeah? So we have the same background, and that's why we behave similarly. And there could be something like these unobserved factors that drive our behavior in a similar fashion. And if you don't have a real structure, a mathematical formulation, you won't be able to disentangle those effects. And what's most interesting is, of course, this endogenous peer effect. In which sense does the behavior, say, inflate or improve by the behavior of the other people in the group? Okay. Let me be very simple in showing the idea of identification and how can we identify those models. This is the very simple Mickey Mouse models. We have two endogenous variables, yeah? That could be a network of two people, if you like. Linear, and there are two exogenous factors, x1, x2. They are a representation. There's the representation which is called reduced form, which is just the solution of that interactive system. You see, this is just an interactive system. You solve that, and this is expressed then in terms of, the y's are expressed in terms of just the exogenous variables. The pi's are called reduced form parameters, but we are interested in the structural form parameters. And this simple example, you see, we have 4 reduced form parameters, but we have 6 structural parameters. So this model is under-identified. We cannot infer from the reduced form parameters on the structural parameters. We cannot estimate such a model by linear regression because it would be inconsistent. Why is it inconsistent? You see, you shock the system here. It has an effect of y1. y1 has an effect on y2. y2 is on the right-hand side of y1, so y2 and the epsilon 1 are correlated. And this is what you don't want to have in interactive systems. In regressions, you have to have explanatory variables which are on the right-hand side. If you ignore that, you get unbiased and inconsistent estimates. You basically do not learn anything from that. This could be something like this y1 and y2 here. This is from my lectures in advanced econometrics. Yeah, so here's price and quantity, but they could also be two reaction functions or whatever. And the question now of identification is basically, can we infer from the data on the true model, the true model behind the data, which has generated those data? And you see here, there are, just as an example, an infinite number of models that are observationally equivalent to these data. So they're always the same data, but three different reaction functions. And that is the identification problem, if you like. Yeah? So what is the true model behind that? And there are conditions to identify that, the true model from the data. This is not a statistical problem. This is a theoretical, mathematical problem. And the first guy who did some research on that was Havelmo, a Norwegian economist who got the Nobel Prize for that identification issues. It's very fundamental in economics, because in economics, everything depends on everything. Yeah? And the distinction between just correlation and causality is absolutely crucial and in economics, if you are not Urs Fischbacher, you usually have non-experimental data, and separation of this correlation from causality is a serious issue. Yeah, okay, and so we will also note that identification and estimation has also certain links. I said it's a mathematical problem, a theoretical problem, but if a model is not identified, in some cases you just even don't get an estimator. Or if it's weakly identified, then the estimator has serious flaws. Okay, just to show you how can we develop rules to identify such a system. I'm staying with the simple model here. Let's assume that beta 1, 2 is 0. That means the second variable has no impact on the first equation. Then the reduced form parameters have a little bit a different form, and you can infer then from the reduced form parameters one-to-one on the structural form parameters. You can solve that system. Yeah? That is an identification condition. And so gamma 1, 2, that would be the peer effect, if you like, in the system that is identified now by the reduced form. So you simply estimate the reduced form, and then the ratio of the two reduced form parameters would be an estimate. A point I would like to make here, you have a ratio of two parameters. That is not completely harmless. Imagine this parameter is very small. Then this gamma would go to infinity in absolute terms. And just going back to that equation, pi 2, 2 is the impact of the omitted variable. So we omit x2 from the first equation in this restriction on the y2. This is called an instrument then. If we exclude this x2 from the regression, then it can serve as an instrument, and this is the basis for the estimator we're going to use later on. An instrumental variable estimator is an estimator that accounts for these endogeneities, these simultaneities, and yields consistent estimates. The second point I would like to make is a ratio of two variables, if they are both, for instance, normally distributed independent, that could be Gaussian distributed, right, if they are independent. And the Gaussian distribution has really fat tails, has no moments. So the statistical inference really gets bad in these in certain settings. How can we separate from cause from correlation? I think that's a very crucial thing in this literature. Very crucial in terms of just comparing these structural models with, say, simple, say, machine learning models, which are just trying to fit a model best. A slightly different example, but it's a very nice one. Yeah, so you want to estimate the causal effect of schooling. Y is some outcome variable, say income, outcome or labor market performance. And S is the educational attainment, in the simplest case, measured as the number of school years. And there are lots of other features in the model, which we're going to ignore for a moment. And we want to estimate this parameter S. Now we have an heterogeneity problem. And the heterogeneity problem is S is correlated with epsilon. So your educational attainment is correlated with everything which is in the epsilon, say non-cognitive skills, cognitive skills, health, and so forth. Yeah? People with higher schooling also have, hopefully, higher cognitive skills. Yeah? So if you just do a regression of Y on S and these other features, you won't get the parameter beta. You won't get something different. And but beta is the causal effect. Why is it the causal effect? Because it's the effect of a change in, say, schooling from S0 to S1. Yeah, you increase schooling by 1 year, and then you want to measure how does income change, ceteris paribus. Yeah, everything equal. And such a model cannot capture that. Why is that so? Well, you have, say, people here with S0 years of schooling and S1 years of schooling. In an experiment, you have where you randomly assign people to S0 and S1, that would be easy. Yeah? So the assignment is independent of the error term, the unobservables. In observational settings, it's not. Yeah? People with S0 of schooling have a different cognitive and non-cognitive skills than people with S years of schooling. So if you run a regression, just the conditional mean, you would get a slope parameter that is beta plus pi 1. Pi 1 is the effect that we call the selection effect, if you like. Yeah? But you want to have beta, the causal effect. And how can you get that? Well, one method would be instrumental variables. That is very popular. You need those variables which affect the system but are not part of the equation you're interested in. Yeah? This was the example from before. So what variable could affect S, the right-hand side endogenous variable, but not the error term? Well, there are lots of empirical studies. People have been very inventive of finding those instruments. It's very popular. Vietnam lottery is a very famous early example from the literature. In the Vietnam lottery in the 60s, young men had to draw lottery numbers, and people with low lottery numbers, they were assigned to military service and the Vietnam War, basically. And that created the effect that people were studying longer, yeah, to avoid the war. Yeah, there are also famous presidents who did that. Yeah, and the thing is, of course, the lottery number is an instrument because it affected the years of schooling, but it did not affect the epsilon, the non-cognitive skills. birth cohort, which cohort you are born in before the due date of schooling and so forth. There are lots of nice examples. So this is the instrument. And we're going to use this idea of an instrumental variable estimator to solve that endogeneity problem that we have in these network models. Weak identification is the case I was mentioning already. Here, if the pi 2 is very small, then you end up in a world that has estimators which are pathological. Yeah? So they follow a Gaussian type of distribution. You cannot do really inference. There are no t-values anymore. These parameters not even converge to a single point if n goes to infinity. So large data sets, large number of observations do not help in these contexts. I think that's also very important to mention, that because we are trained in standard statistical models that if the data set is very large, everything is beautiful. It's not in these settings. Yeah? It can still suck. Here's just some example. This lambda is basically the parameter pi I was mentioning before. And I changed it a little bit. Yeah? So you see, this is the distribution of that estimate of this endogenous parameter, if you like, the peer effects parameter. And you see slight variations of this parameter create huge problems. This is already not normally distributed. In the nice world, it should be normally distributed. You see it has already very fat tail on the left. It getting larger here. You look at the dimensions. And with lambda 0.4, you have a dot here, and sometimes you have outcomes which are 350. Yeah, so it's a serious issue that you have to account for in these studies. Yeah? So, coming back to the network representation, we're going to use a network presentation that is called a compositive model. We have two types of peer effects. One is a local aggregate peer effect that is represented by A. The Aij's are just the elements of this network matrix, and the G's, which is the row normalized network matrix. Then we have all these other animals there, the exogenous peer effects, exogenous effects, and we have here effects at the network level. Yeah? So that these are variables that are describing the network, classroom effects, if you like, in our study. They can be observable or unobservable. We account for that, but we are not really interested in that. Mostly we're interested in the betas. So that is an interactive system of these n agents in a network. And the presentation of the networks is twofold, and we account for both of them. And in matrix notation, that looks a little bit simpler. So we are basically interested in estimating those betas. And we could give them a theoretical interpretation. It looks a little bit ad hoc-ish in the first place. You'd simply say the y depends on the y's of the others, of your peer group. But the theoretical foundation could be given by a game theoretic model. Where is it? Here. You have a utility function that measures the utility of some action in y. And there are two components, a benefit component. Yeah, so the benefit depends on this action of individual I in network L, but also on the activities of the other people in the network. Yeah? So, and there's a cost component doing that activity also has costs, and these costs are driven by your own activity, but also from the activities of the other actors. However, if you see here, it's the difference between your activity and the activity of the others. This is kind of norm behavior. Yeah? So G, remember, is the row-normalized adjacency matrix. If you do not deviate from the norm, from the average, then you profit. You have a certain utility. Yeah? So the question is, what of those two factors, lambda, are stronger? Is the behavior driven by similar behavior of individuals? Is it driven by the fact that you don't want to deviate from your social group? Or is it driven by the profits that you are getting from the others? Yeah? Okay. Coming back to the initial graph, I introduced already the adjacency matrix. What will be important to construct instruments are the higher order adjacency matrices. This here is just A times A. This is the second order adjacency matrix. And there will be, of course, higher order adjacency matrices. And it turns out that you can use those higher order adjacency matrices as instruments. The information, what the peers of the peers are doing, can serve as an instrument. Yeah? And here's just a mathematical presentation of that. You see here are the higher order adjacency matrices, and they affect these endogenous variables. They serve as an instrument. Yeah? So what we're using then in order to construct this IV estimator is using those instruments from the higher order adjacency matrices. Another thing which I find very interesting from that literature is once you have modeled these interactive behavior, you can get a lot of measures out of that describe that behavior. One is the social multiplier. That is the overall effect of some intervention. Say X is an intervention, and you want to see what is the effect of intervention X on outcome Y. The direct effect was gamma, yeah? But through the others who also profit from an increase of that intervention, the overall effect gets larger through the peer effect. So if beta is very large, so beta should be positive, but smaller than 1, you see it inflates the activities, the profits from that activity. That is called the social multiplier. Okay, so what we are doing in that paper is we are considering several networks, and we estimate these networks in a two-step procedure, which we call minimum distance IV estimation. In the first step, we do IV estimation for the single networks, yeah? Get the parameters. And the second step, we have a minimum distance estimation, which collects all the parameters, the estimates from the first stage, and we impose a structure on those parameters and check whether they are similar or not. And this is given by this equation. So intuitively, we reduce the dimensionality of the first stage estimates optimally to get the structural parameters. What's also innovative in our approach is that, as the title said, we are talking about heterogeneous networks. And that refers to two aspects. One is that we have different networks, this with the adjacency matrix A and the adjacency matrix G. The other aspect is that we also want to have heterogeneous peer effects. So we make the peer effects a function of observables. Why could the peer effects different in different networks? Well, in our application on school classes. There is, for instance, gender decomposition. That could matter. What is the gender ratio in that class? Do the peer effects differ if there are more girls in the class? The class size, maybe the kids do not cooperate so much if the class is very large and so forth, right? And the structure of the network itself. Yeah? So the paper I'm referring to is not yet finished. You see, this is just the cover sheet. January 8th. We hope we finish that by, say, at end of the month. Livia is here, one of the co-authors. And so what are the novel features? We developed this new estimation approach, the IV minimum distance approach. We consider both local average and local, there's some word missing, local aggregate peer effect. We have this network heterogeneity in terms of the peer effects, which are heterogeneous. And then we study in particular the role of gender composition in classes and class size for the peer effects and then for the educational attainment. Our study is based on data from 121 school classes, 68, and then we have 86 classes. Yeah, and we look at 10th graders at year 15, which is kind of nice because 10th graders don't have this coursework. So they are really working still in a classroom together, more or less, at that time anyway. We have different performance measures. I just want to report on those on the GPA score, the Allgemeine Durchschnittsnote, as the performance measure, and then we have quite interesting background variables features, IQ, which is very rare in social studies, that you have the IQ of the people in the sample. Of course, the education of the parents and so forth. So how do we get that information? Well, the guys who collected that survey, they gave every student a sheet of a table where they had to cross. Who is my peer? Who is my buddy in the class? And we use that information. In fact, they have more information. There is also who's my enemy in the class. This information we have not exploited yet. And to give you some graphical impression about heterogeneity, here's just the largest and the smallest school class. The circles are girls, the squares are boys. The colors indicate the grades. You see a dark grade means it's a bad student, a light grade is a very good student. And here, well, that is this large class, and this is the smallest class we have in our sample. And what you very often find that the bad students, here these are dark points, they're not very well collected in the class. That's generally the case you will see from eyeballing. And so just briefly on the estimates, these are the local aggregate peer effects. That means the size of the group matters for your peer behavior. Class size has the desired negative impact. That means we have German grades. Negative impact means they get better. They have a lower grade. Yeah? And gender decomposition matters. The more women are in the class, the higher is the peer effect, the better are the grades for the whole class. We also introduce some network measures. Network density is the number of connections divided by the total number of connections. So the denser the class is, the worse the grades. And cluster is the the number of transitive triads by the total number of transitive triads. So you have to interpret that coefficient as given a certain network density. Is it good if the network is clustered, if there are several groups in the cluster? So that relates a little bit to what Ulrich Brandes talked about. And that is bad. Yeah? If there is certain group behavior in the network, in our findings at least. And for the local average effect, the effects are basically the same. You would say, well, that is not so surprising, those results. That's intuitively clear. But let me make 2 points. One point is there are zillions of studies in education science and educational economics which cannot prove that the class size has an effect on the performance in class. We always think that the smaller the class, the better the students. Empirically, it's very hard to find. You find that in classes in Africa, if you reduce the class size from 80 kids to 40 kids, that matters. But usually, if you find significant effects, they are very small. Yeah? If they are significant, they are very small. The other point is, once you have found those, you're just fitting something, school performance of a kid on the class size on the right-hand side, you do not learn very much from that because you don't know where that is coming from. Yeah? Here, that has a slightly different interpretation. We also have a class size level effect, which we partialed out here. So we account for that, but we don't have an estimate. And here is just the class size effect through the peer behavior. Yeah? So it matters. We have an interpretation for the class size effect. And the same holds for gender decomposition. Okay. Other characteristics are very obvious. Yeah? So IQ should help. And they are basically for the controls. We don't discuss that much. We have, then the nice thing about the model is that it's very general. There are lots of sub-specifications, models nested in that general compositive model. So we can test, for instance, the heterogeneous aggregate model against the homogeneous one, and the same for the local average model. And we can compare the aggregate compositive model against the aggregate model against the compositive model. And it turns out that our specification is dominating more or less. Yeah? So the p-values of 0 always means you should always go for that heterogeneous model rather than for the simpler versions in the literature. Okay. Further findings, we have different outcome variables. It's very similar, that's why I don't present it here for mathematics and German. Heterogeneity matters. Peer effects in homogeneous model specifications are often insignificant. So, and there are a handful of studies using those techniques, and they hardly find significant effects. They estimate the peer effects, but they are not significant. And maybe it's because they don't account for heterogeneity. I said that this one, and the final point is we are using the peers of the peers as instruments, but you could also use higher order peer effects or adjacency matrices, but these become weak. Yeah? So there is a trade-off. One can study mathematically. More instruments is better asymptotically. Yeah? You get a precise estimate asymptotically. But in finite samples, if the instrument is weak, you have this weak instrument problem about the distribution. So it's not quite clear how to handle the number of weak instruments in that study. We have some proofs on that, but I don't want to talk about this in this context. So we can at least show that if there are a few instruments asymptotically which are strong and many are weak, the strong ones asymptotically dominate. Extensions of that literature. So this was a cross-section of different networks which we're using. Very often we have a time series of a single network. Yeah? So you have that, for instance, and Tobias Kerner has that, who is from education. And so they observe a peer group over time. And we have some ideas that will be the next paper to study that in a generalized autoregressive score model that is basically kind of nonlinear Kalman filtering model. We study the network formation. That is also an issue in your research. Yeah? So here in this study, we say there is a network, and given that network, what is the behavior? Yeah? But you could also ask, why are these links there, and what determines these links, the zeros and ones? That is a pretty easy extension, at least from a methodological point of view. And we could also do that with our data. We have an idea how to get a sparser specification to unify those two approaches, the local average and the local aggregate model, into one model where simply a single parameter tells us which model is contributing more to explaining the data. And we have some idea of individual specific peer effects parameters. So far, the peer effects parameters were just network specific, and they were driven by network specific factors, but you could also say that every person in the sample has a different peer effect. That would also be handleable quite easily. So that will be do for the moment, and thank you very much. I'm looking forward to your questions. Thank you. Oh, I have co-authors. These are my co-authors. Sorry for that. Yeah.
Can you just say again, you said like you have evidence that the class size has an effect on the outcomes in your study. And you said it's because of these peer effects that you could measure?
In our study, we just looking at the effect of the class size on the peer effects. We account for the usual class size effects, but we find out that the larger the class, the lower the peer effects. The less people profit from the others.
I have a question concerning the adjacency matrix. Could you explain? So you use it as an instrument. Could you explain kind of both sides? So why is it? So it's kind of clear that's correlated with the. So that square is
correlated with the G.
Yeah. With the adjacency matrix itself, but it's not so clear why it's uncorrelated with L.
Well, that is our endogenous variables, G times Y. Yeah. So basically, the average scores people have the average score of the peer group. Yeah, in G times Y, and you can express just solving that system. You have this inverse here. Well, there are lots of identification conditions which I didn't talk about. Yeah? So you have to invert that, and this inversion does not work. For instance, if the network is very dense, yeah, then that also means then the instruments become very weak. So there is really one-to-one correspondence between the type of the network and the quality of the estimator. Yeah, and so this is why, expressed in terms of these higher order adjacency matrices, Yeah, and you see here is just the expectation of that, and you can express for the right-hand side, this would be kind of the reduced form. Yeah, and it turns out that the reduced form is a function of these higher order adjacencies, technically speaking. Intuitively, yeah, the peers of the peers are exogenous here in that at least do not affect the epsilons. Yeah, so.
I think I have a clarification question on what the peer effect actually means. Because now you said the smaller the classes, the more people profit from one another. But it can go both directions, right? Peer effects can go also negative. So isn't it the more they depend on others' performance? Is it like a contagion of performance in these networks that goes both directions, the good and the bad direction?
Here the peer effects are positive. Yeah? So the betas are always positive. It's a positive contagion.
But that also means if my peers are bad, then my grades also become worse.
Yeah, the dependency, yeah? Yeah, that's true.
So
it's yeah.
Okay, so then I understood correctly.
Yeah, it's just if your peer group has better grades, you also can become better, yeah, in that sense.
So you said you were planning to extend it to longitudinal measures.
Yeah.
So what will be the advantage compared to already existing algorithms like stochastic vector-oriented models? So will it be
Do you have X's in your models? Covariance and those kind of things? A real model? Yeah. I don't know. I don't know too much about that, but I'm interested in those GAS models, the generalized autograph score models. It's a very easy way to model time-varying parameters. So that's the nice thing about if you're that general, as I'm doing also financial econometrics, and they have these time-varying parameter models which evolve over time. That's now quite a nice way of modeling these without great computational burden. Yeah, so you get a stochastic law of the peer effects, if you like. And what we are trying to do is, this is about stress in school classes. And Tobias is interested in he's imposing stress on the kids, and the question is how they cooperate over time when they are subject to more or less stress. Yeah? So that's what we want to measure. Yeah.
How do you bring out the causality? What constitutes the causality in your model?
The simple idea of causality in this is a ceteris paribus. Yeah? So you change one variable and hold everything constant, yeah? Like you do in a lab experiment. Yeah? And if you ignore these simultaneities, these endogeneities, you get something estimated, but it has a different interpretation, like in this schooling effect. Yeah? So here, what you're estimating, if you just do a regression, is this pi1 plus beta. So the actual causal effect plus the selection effect that you have better students in a higher level of schooling. Yeah? And that's very important if you don't have experimental data. Yeah? So this, lots of brain is devoted to these kind of things in our area.
In more general comment or question, so I mean, as you know, we have a lot of trouble getting this into ecology.
Yeah.
But I think it's really important because I would say biology, ecology has not really embraced these models because they were just too complicated for most people. Now, and you've seen the comments that we get when you apply these models. The ecologists tell you, well, you know, we don't. I mean, these methods are solid. We don't know. And the seismologists say the same. And but the question is, as a cluster, how do we go ahead and? Because I think it's fundamentally important that we include these models in ecology. How do we do that?
Yeah, well, I try to always say, but there's huge literature now, hip literature, machine learning. In our cluster proposal, we had, I think, this buzzword 60 times. Yeah, but nowadays the machine learners moving towards interpretable machine learning models. Yeah? So just fitting and forecasting is for scientists who are really interested in a substantial question, like educational guys, biologists. It's not enough. Yeah? So we need a mathematical structure. Yeah? So that's both type of models have their their nice properties, and these kind of things you only get out if you have a impose a certain structure. And the clue is probably to be most general, yeah, but still having a structure that you can interpret. Yeah? So this is of course a linear model. You could be more general in certain dimensions, yeah, but you need a structure. And the structural models, they have the advantage that you can interpret them. Yeah, it's not just we find a correlation, and yeah. So we always have to have that in mind. There is room for both type of models, and if you just want to forecast, then you don't care. Yeah? The forecasting guys. I don't know, we don't care where that comes from, why the X has an impact on Y. It's a black box. But here we want to look into the black box, and then we have to impose structures. The exclusion restriction I was mentioning as an example to get instruments is something like that. And exclusion restrictions cannot be testable. Yeah, so by assumption. Because the estimator only exists if the exclusion restriction is there. But you can have good reasons for that. Yeah? And you have to be a good economist, biologist to say, well, that is really very unrealistic. That's why I can assume that this parameter is 0, and then you can identify the model. Yeah? But there are costs to that. Yeah? So structural modeling, definitely. So it really depends on what you want to do with that. Good. Yeah, thanks.